Okay, yeah. Okay, so it's a great pleasure to have Professor Urbasi Sinha give the monthly colloquium. Of course, we all know her. She's our friend and colleague from the Raman Research Institute, and she heads the Quantum Information and Computing Laboratory there. Um, and I guess today she'll talk about some of the interesting work that they've been doing over at her lab. I just wanted to sort of maybe highlight some of the scientific recognitions that she's received, which include the and in 2018 she won the ICTP ICO Galileo Dinardo Award in Optics. And she's also been recognized as one of Asia's top 100 scientists by the Asian Scientist for the year 2019 and was awarded Simon's Emmy Noether Fellowship at the Perimeter Institute. So I hope we'll have a very stimulating, interesting talk by Professor Urbasi Sinha. And so I now pass it over to you. Please take over. Thank you.
Thank you very much. Thanks, Vishal, for this very kind introduction. And of course, Vishal and Shubhro for the invitation to talk in this colloquium series. And Deepali for her immense patience with dealing with size of abstract and all that there is to it in logistics. So thanks a lot. It's a great pleasure to be speaking in this colloquium series. As mentioned, I will be talking about some of our experiments, but focusing on one of them, which is the most recent one, which is called quantum state interferography, which is a quantum state estimation technique that we have devised and established experimentally in our lab. Right, okay, yeah. So this is, a snapshot of various experiments as they are in progress in the lab. And of course, on a good day and a good year, it would be very nice for you guys to come and visit our lab and see some of these things. But at the moment, of course, we cannot talk about physical visits for some more time. So this is how things look in an optics lab. And this is also a class 10,000 clean room, which means that we have less than 10,000 dust particles per cubic foot, which is essentially, to avoid the interference effects with dust and just stick to the interference effects that we really want to see. And so that is the idea of the clean room. So what we do is work on different applications of photons. Okay, so we are a quantum optics lab, and our focus is working with photons and their applications in quantum computing, quantum communication, quantum optics, of course, fundamental optics, as well as quantum information processing. So these are all the various areas that are represented in our lab. And in fact, if you're interested more in finding out how to actually make these photons, because it's not straightforward. You just don't take a light and then dim it down and out comes a photon. There is a lot more that goes into it in terms of how to make these photons. And so please have a look at this review that I was invited to write, where I have covered different aspects of photon sources. This is a picture from the lab, which is of our own, one of our photon sources, which is based on what is called spontaneous parametric down conversion. What is interesting here is that you can see that these photons, they come out in the form of cones, so there's a nonlinear optics process. And so if they come in the form of a pair, so if one of them is here, the other will be here. But now if you look at this intersection point, you don't really know which cone it belongs to. And that is what actually defines the entangled state. And so if we are interested in applications which involve entanglement, this is the kind of source which we make. And so we have several different types and several different applications therein of these photons. Okay, so going on to the main topic of today's discussion, it is of course about quantum state estimation. And the first thing that we would like to understand is why quantum state estimation? Why is this an interesting or important topic to think about? Now, the wave function is of course used to completely describe a quantum system and is central to quantum theory. In theoretical calculations, one can assume a form of the wave function and then proceed with the calculations, right? That is what we do. If we are doing theory, we just assume, okay, here we have a pure state, and then we apply whatever operations we need to do and proceed with a life. But what about experiments? Okay, for example, let's say quantum computing. So in quantum computing, of course, you begin with, let's say, the state of a qubit. Let's say we assume, okay, we have a pure state, and then we apply these myriad gates, and out comes these protocols, and everything is okay. But then the precision in knowledge of the state of the system actually leads to precision in all that follows, right? So we just can't have this bent of mind as we would do in a theoretical calculation where what we assume is what we write down. You know, in experiments that is not going to happen. So we simply cannot assume something and think that our assumption is right. If we assume a pure state, we have to verify that, you know, this state that is actually what we thought it was. And so that is, of course, the most important reason as to why, quantum state estimation is important from an experimental, practical, or technological perspective. Of course, once we know the density matrix, we can calculate many important quantities. The reduced density matrix can be used for calculating entanglement measures, for instance, like entanglement entropy. So if you now think about a mixed state, then of course you have the density matrix. If you reconstruct the density matrix, then you can do many important quantities will come out of it as well. Okay, and so these are all reasons which make this an interesting and important thing to do, to estimate the quantum state as precisely as possible by using commensurate methods. In our work, we have used one of the most fundamental phenomena in quantum systems, that is interference, to devise and experimentally demonstrate a new method for quantum state estimation, which of course we call quantum state interferography. So here we have estimated the quantum state by using interference as a tool. And of course, if you think about interference is a phenomena which is at the heart of things quantum, right? For instance, Richard Feynman very famously said that if we choose to examine a phenomena which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics, he would choose the double slit experiment. So in reality, it contains the only mystery. It's a rather popular a thing that he had said. And also carrying on to more modern times, it was voted. The double slit experiment was in fact voted as the most beautiful experiment in physics by readers of the physics world a few years ago. So there is interference is something which is inherently associated with quantum phenomena. And many things have been done using it, by it, for it, and so on. And what we are doing is, in fact, using it in a completely new avatar, where we are using it as a tool to estimate another very important quantity, which is, of course, the quantum state itself. So this is how we are, it sort of sums up towards quantum state interferography. Okay. So what is our central question? Our central question is that suppose we have, let's say, a beam or a stream of particles, and now we want a device and a state readout. Can we have a device with which, without any change of internal settings by the user, we can determine the quantum state of the system? So can we have a black box approach to state determination or a single shot state determination? This is the question we ask and in fact answer through quantum state interferography. This is what forms the crux of the matter, that we have a device with which we can basically read out the state in a single shot approach. Okay, so having said that, of course, determination of the quantum state is something which has been happening for several years now. So there are different techniques, and so I just wanted to walk through some of these methods for quantum state determination. The most popular one, perhaps, is what is called quantum state tomography. Okay, and this is a nice review which you can read about the details. But essentially, it is similar to this thing that you see here down right, which is in fact somebody going in for a CT scan. So when you do a CT scan, let's say a CT scan of the brain or something like that, what we do is we actually take projective images of the brain, different projections, and then stitch them together to reconstruct this image of the brain. This is a non-invasive technique because, of course, you don't really want to do something to the brain per se. You just take different projective images, reconstruct, and you get this image. And so this is what we do with the quantum state also in quantum state tomography. This quantum state, we perform different projective measurements and of course, we know what these measurements would be. And then from these results, we reconstruct the quantum state. And this is what is called quantum state tomography, the most popular way of determining the quantum state. However, the problem with quantum state tomography as it stands is that, the number of measurements that is required actually scales in the order of d square. Okay, so if your state has dimension d, then it is you require d square minus 1 number of measurements to reconstruct the state. So for, let's say, a 2-dimensional state, you will require 3. Then for a 3-dimensional state, it becomes 8, and so on. So you can see that it really scales up very rapidly as the dimension increases. And that by itself is not very nice, because we don't want to do so many measurements. Believe me, if you're an experimentalist, you want to do the minimum number of measurements, because with each measurement, you have an error associated with it. And so the minimum number of measurements, if it gets you, the thing that you are after, that is, of course, always good for you. And so here, QST does not really work very well when you go to higher dimensions. So in fact, this particular paper here actually tells you what is the minimum number that you can do if you want to reconstruct a pure state. And so that is in fact 5D minus 7. So they brought it down. So if you put in some assumptions, you can bring it down, but not better than this. Okay, and so this is what they did. And so best scaling for pure state is 5D minus 7, but for mixed state, still remains d square minus 1. So we need alternative to quantum state tomography. And so one of the first ones that came up with such an alternative was what they called this direct measurement of the quantum wave function. And this is a technique by which they used, sequential measurements to actually directly measure the wave function per se. And these measurements involved what is called a weak measurement. Okay, I won't get into the details here, but then here they directly measured the complex wave function by performing a sequence of measurements, one of which is a weak measurement. And this was done for the spatial degree of freedom of the photon. And later, another group actually did this for the polarization state of light with direct measurement. And this is how it is done. So this is what is called the weak value. And if you measure these expectation values, then you end up with this quantum state. And this was for a higher dimension. But then came, this realization, and this particular work showed that, they did a direct comparison between direct state measurement and tomography. And they found that indeed, this direct state measurement using weak measurement is much less precise than tomography. And there are unavoidable errors that happen in the reconstruction using this weak measurement technique, okay? And so then came these set of works where they actually replaced the weak measurement with strong measurements, which give a better direct measurement of the quantum wave function. And so several works followed. And so these were all these direct measurements with either weak or strong measurements, okay? So now that brings us to quantum state interferography, which is our method, where we have, as I mentioned, used interference as a tool to measure the quantum state. And here, it's a method, an interferometric method, using which an unknown quantum state can be inferred from the visibility, phase shift, and average intensity obtained from an interference pattern. Okay, so no weak measurement in this case. It is not a direct state measurement. In a direct state measurement, what they do is they actually have many measurements, but then they get the wave function as a result. What we are doing is we are doing a single measurement, and we actually get the wave function as through post-processing. So we are minimizing the number of measurements, and these direct state people, they minimize the number of post-processing. But of course, it is to our advantage to minimize the number of measurements, because then we minimize the errors, because post-processing of an interference pattern is not that difficult and or error prone, okay? And so we have a new single shot state estimation method using interference as a tool. Okay, and this is how it looks in the lab actually, just, this is your interference, this is your Mach-Zehnder interferometer, this is the input state, and of course we will go through exactly what we are doing here, but this is the general idea, and here you get the interference pattern from which we reconstruct the quantum state. Okay, so the basic idea behind all this is, kind of captured in this slide. So suppose this is, a form of the density matrix. So this is the form of the density matrix. And this is what we call a spin ladder operator. So, you're this creation and annihilation operators that come across. That is a spin ladder operator, sigma minus. So if I am able to measure two expectation values, one is expectation value of pi naught, which is a projection operator, okay, and this expectation value of what is called a spin ladder operator, that is the sigma minus, then by evaluating these two for an unknown state, I can determine the density matrix rho. This forms the basis for quantum state interferography. So these are the two expectation values which are of interest. But of course, when I say that, you realize that I'm talking about the expectation value of sigma minus, and this in fact is a non-Hermitian operator. So,
sorry,
yes.
Can you just tell me what this pi naught is projected to? I missed it.
Well, pi naught is, in our case, is projected to the horizontal degree of freedom of a photon. We will come to that. I mean, here it is just a projection operator. In, it's the general description. I'll say what we are doing in the experiment in the next couple of slides.
Yeah, with respect to your density matrix, what is it? Is it just
it's
1,
just,
0, 0? Yeah.
Yeah, it
0,
is just
0, 0?
Yes.
Okay.
Exactly.
Okay. Thanks.
Well, I have the form also later, but that is exactly what it is.
Okay.
Yeah. So now, as I was saying, so pi naught of, I mean, this is not a very difficult thing to do, this projective measurement. But the sigma minus is a non-Hermitian operator. And so how exactly, if this is what we need, how would we do that? How would we measure the expectation value of a non-Hermitian operator? And so in order to answer that, in fact, this is one of our previous works here, where we have shown how we can measure non-Hermitian operators via what we call weak values. And so this is something which we also evoke finally in quantum state interferography. So this is this forms the basis. So okay, so A is my non-Hermitian operator, and if I now use polar decomposition, I can actually decompose it into a product of a unitary and a Hermitian. Okay, and so this A is U times R. So now if A is this sigma minus from the previous slide, then I can see that this can be decomposed into this unitary 0, 1, 1, 0 times this Hermitian 1, 0, 0, 0. Okay, and so this 0, 1, 1, 0, as you know, is the sigma x operator, and this one is this projector. So now, if so, a non-Hermitian can be decomposed into a product of these two. Okay, and so what happens then? So if the sigma x, this is actually the Jones matrix formulation of what we call a half-wave plate. Okay, and so a half-wave plate, and this is a Jones matrix formulation of what we call a polarizer. Okay, and so for theta equal to 45, this particular matrix reduces to 0, 1, 1, 0. Okay, and this is your half-wave plate. This is how it looks in the lab. Theta equal to 45, with respect to the fast axis, you will get this matrix. And for theta equal to 0, this matrix for the polarizer reduces to 1, 0, 0, 0. Okay, and this is the polarizer. So now this, of course, is rotated to give me the horizontal projection. Okay, so this is a linear polarizer. So essentially, what this slide tells you is that I can decompose a non-Hermitian operator into a product of a Hermitian and a unitary, and these are all realizable in the lab. A half-wave plate with its fast axis, 45 degrees, with the angle 45 degrees with respect to the fast axis, gives me the sigma x, and a polarizer which allows horizontal polarization to pass through gives me my pi 0. Okay. So now what we had shown earlier is that, as I mentioned, that we would be able to measure this expectation value of the non-Hermitian operator by measuring what we call the weak value. So what is a weak value? So here is the definition, of course, of expectation value. So this is your operator A, this is psi A psi, yeah. And so now I know that A can be written as U times R, as we showed earlier. So if this is, now you can just multiply and divide by psi U psi. And so then you can see, this is just an algebraic manipulation. So this particular quantity here, that is psi U R psi by psi U psi, is what is called the weak value of R. Okay. And so essentially it's a transition amplitude. So instead of, so what is the difference between these two is here you have the initial and the final both having the state psi, but here we say that we are in a pre-selected state psi and a post-selected state U psi. Okay, I won't get into the details, but the idea is that this weak value multiplied by this inner product is giving you the expectation value of the non-Hermitian operator. So then if that is the case, so far so good, but then for state determination, one needs to know this as well. And that is a problem, right? So if I actually need to know this in order to determine psi, then there is a circular argument that we are coming to. So we actually solved this argument in a later work where we showed that we can in fact measure this average of this non-Hermitian operator with weak value without using weak measurement in a Mach-Zehnder interferometer. And this is where your interferometer first comes into the picture. So using an interferometer, I can actually measure this expectation value without worrying about weak measurement or post-selection. And so this is what we had shown in an earlier work. And so this, again, is your Mach-Zehnder interferometer. And you already saw the picture from the lab, but then this is for the previous experiment where we had measured this expectation value of the non-Hermitian operator. So what did we do? So here we have the state preparation, as you can see, and here is my half-wave plate, the U, and this is your, either you can use a polarizer which is allowing a horizontal, or you can use what is called a polarizing beam splitter where the transmission is always of horizontal. So they are actually equivalent. And so this is what we require, and this is the Mach-Zehnder, and the intensity at the detector is then given by this expression. So this actually is involves the expectation value of pi 0 as well as the expectation value of sigma minus. And here, of course, there is some math, but then for the sake of, this is of course a colloquium, so I will avoid the detailed math, but what you can see is that this intensity in fact does boil down to this expectation value of this R square and this mod Z, where Z is the non-Hermitian operator. And what we usually measure when we measure, of course, interference is the visibility, which is the maximum of the interference minus minimum divided by the maximum plus minimum. And that actually is shown to be essentially this. So that is 2 mod Z by 1 plus expectation value of R square. So now, if I measure the visibility and then, of course, phi as the phase shift, which is caused due to the action of R and U, then I need to determine this expectation value of R square separately, where of course it is the half-wave plate here for us. And then with the knowledge of the state psi through the operator R, I will be able to get this non-Hermitian operator. So in this particular work, what we had of course done is we knew what state we were using, which was in fact a 45-degree state, that is 1 by root 2 H plus V. And this was the operator that we measured, where, this was of course the half-wave plate, and this is your polarizer, okay? And this is the result we got. So this is the expectation value of this non-Hermitian operator as a function of the half-wave plate angle. And of course, we got very good match between theory and experiment. And we also measured the weak value in this case. And also went on to show that if you measure the weak value using conventional weak measurement, you actually don't have a very good match at some positions. Whereas for this interferometric method, you get a very good match for all values of this half-wave plate angle. And so this was our previous work. So what we have established so far is that, we have a method by which we can measure this expectation value of sigma minus using an interferometer. Now we will put all this together and figure out how we can use all this knowledge to infer the state, the quantum state itself, using interference pattern. Okay, which is of course quantum state interferography. As I was mentioning in the beginning, this tomography requires d square minus 1 measurements. For pure state, it reduces to 5d minus 7. We have shown in our work that for d-dimensional pure state reconstruction, our method requires d minus 1 interference patterns or interferograms. And this can be obtained with as low as 2 interferometers. So we have a very, very good scaling advantage here compared to quantum state tomography. And for, essentially a qubit, we can do this in a single shot measurement. What is a single shot measurement? It means that it's essentially a black box. You have an interferometer, you have an input state, you have the output, that's it. You don't need to change any settings in your experiment to get this quantum state. So the settings remain the same. And so it's a single shot state estimation technique, okay? And so if I compare it in terms of the dimensional advantage, you can see that, of course, for 2-dimension, QST would require 3, and QST with an assumption is also 3. For us, it's 1. We require just 1 measurement. But as you go up, of course, it becomes more dramatic. For d equal to 100, for instance, these QST would require 9999, but QSI is essentially going to require 99. So there is a tremendous scaling advantage in quantum state interferography. Okay, so now going on to using all this information towards finding the quantum state. So our aim, of course, is to infer the unknown polarization state of an ensemble of identically prepared qubits using a single interferometer. So here you have a pure qubit state. And so this is your usual state representation where you have a theta and a phi. So this is the pure state. And if you have a mixed state, of course, it's the density matrix representation where we have an additional mu, which is representing the purity of the state. Okay. And so what we want to do is we have to determine this theta, phi, and mu from an interference pattern. So all this will be determined from that interference pattern. And then we'll be able to get the form of the quantum state. Okay. And so this is again the interferometer. It's a similar picture to the one you saw earlier. Here you can see this is your pi h. So this is the projection. So I'm projecting it to the horizontal. Here I have the sigma x. And so the operator here, of course, is the sum of these two with a phase, because of course, when you have an interferometer, you can have a phase difference between the two parts. And so that is given by this epsilon. And so this is what you get. And then if you go through the math, you will realize that for the pure state, your interference as a function of this phase difference is given by this formula, which of course depends on theta and phi. And for the mixed state, it is again given by this formula where we also have the mu coming in, which is of course the mixedness parameter. Okay. And so this is the most important, I would say, slide in terms of remembering how to go about this. So this is for the mixed state. The mixed state is of course the more general case. So interference as a function of this phase difference is given by this formula, which please go through this paper to get the details of the math. But then what are we determining here? So there are three quantities which we are going to measure from this interference pattern, which will actually give me these three parameters. Okay, and what are these three quantities? One of them is the phase shift. So this is the value of epsilon for which my intensity is maximum. Okay. The second is the average intensity. So I can of course always measure the average intensity by averaging over all values of the phase difference. And then of course the visibility, which is the most common thing to measure in an interference pattern, which is going to be the maximum minus minimum by maximum plus minimum. And so as you can see here, so the phase shift is of course simply given by this value of phi for which ID is maximum. So this I can get. Then what I would go on to measuring is in fact the average of the intensity. So if I measure the average of the intensity, I will get theta. And with that knowledge of theta, by measuring visibility, I can then get mu. Okay. So by measuring one interference pattern and calculating the phase shift, average intensity, and visibility, I will be able to get theta, phi, and mu. Okay, and so this is what is very important here to realize that it's not like, we are doing something, okay, quantum state tomography has a d-square dependence. How are we getting away with doing much less? The idea is that we are actually measuring much less, but gaining a lot more information from it. So one interference pattern is actually giving me all this information. And that is the, I would say, the clever way in which we are able to determine the unknown quantum state. Okay. And so this is how, of course, it looks. Yes.
Can I ask you a nice question? This number d square minus 1, I presume it's coming from the total number of local observables.
Yes.
But why actually do I need that many numbers? Because if I have a d-dimensional space, naively I need 2d minus 1 real numbers.
So see, the point is that so d square minus 1 is coming from this. So if you have a density matrix, so think about 3-dimensional case, right? That is a little more interesting. So you have 9 elements, right?
Let's talk about pure states.
Pure state is also fine. Okay. So pure state, as I showed you, the advantage is that in pure state you require 3 measurements, which is the minimum that you can do. So that is the 5D minus scaling, as I mentioned. So you have 5 times 2 minus 7. And then for the, so what was the actual?
So the question is that
so there are 3 parameters, right? So
if why is it not 2D minus 1?
Well, it is d-1 in our case, of course, but how can it be a d-1 in tomography? Because, of course, in tomography, you actually have to do 1-1 measurement to get each of these quantities. So if you want theta, phi, and then, of course, there is the overall scale and normalization as well, which comes in, you see. So that is why you require 3. So it's this, if I go back to this form, which is here. So then, of course, this is my pure state, right? So I have theta, I have phi. And then, of course, we always have an overall factor, which we have to also determine. So that is why I cannot do better than kind of 3. So for each of these, so what we do in tomography is for each of these, we require a separate projection. And that, of course, is by using the Poincaré sphere and so on. So you can actually do, so think about it in terms of the Pauli matrices. So you will require a sigma x, sigma y, and sigma z. Did you?
I think for the d equal to 2, all these numbers 5d equal to 5d minus 7, etc., all are same.
Yeah.
But
they're all same, exactly. They're all the same.
I can ask
there is no advantage.
Again at the end of the talk.
Sure. But then for, as you rightly say, for d equal to 2, you don't really gain much with the 5d minus 7. It's only when you go to d greater than 2 that the 5d minus 7 is kind of better than d square minus 1. But in our case, of course, it's d minus 1, which is a 1, if d equal to 2, and it scales linearly. Okay, so I was probably here. Yeah, so as I was saying, so all I need to do is actually measure these 3 quantities from my interference pattern, and then I will be able to reconstruct my, in this case, I'm talking about the general mixed state, right? And so this is, of course, how our interferometer actually looks. So this is a Mach-Zehnder interferometer, and here you have, the initial state. And so I actually can, so what we have done is that we have, of course, prepared all possible initial states. So we have actually gone through the entire block sphere. So you have a half-wave plate at a certain angle, followed by a quarter-wave plate at a certain angle. So by going through rotations of both, so keeping one fixed, rotating the second one, and then so on and so forth, you can actually traverse the whole block sphere. So which is what we have ended up doing. And so that is why you have this here. And then, as I was saying, I won't go through too much detail here, but then, of course, the important point is that we have the projector in one arm, and we have the sigma x in the other arm. And what we ended up doing is actually, instead of Mach-Zehnder, what we used is what is called the non-collinear displaced Sagnac interferometer. And again, this is a detail, but this is actually an interferometric technique which does not require additional phase stabilization, which is very useful, which Mach-Zehnder actually does. So this is what we ended up using, and varying the phase in the space domain instead of the time domain. And this is how an interference pattern would actually look on your camera. And so we have used helium neon laser and so on. And so these are the different, so I'll skip the details. So this is an example of an interference pattern. So this is the intensity as a function of, the detector screen. And so this is how it would look. And we have taken several of them. So, 100 slices, 5 each, and that is to gain statistics. And so this is essentially, this is how things look. So if you measure phase shift as a function of these half-wave plate and quarter-wave plate angles, then, the solid line is your theory, and this is your experiment. So we have, of course, done it for several different angles, and you can see that the match is pretty good, except that, of course, at these points where you are at the pole, the phase is not quite defined, and that is why it shoots up. Those are the points where you don't expect a match. Here you have the average intensity as a function of alpha beta. Here you have the visibility as a function of alpha and beta. And so this is, of course, all these graphs in one, but this is the important one here, where I will, we have plotted the fidelity, okay? And so this is your general form of the matrix. And so if you now find out the fidelity, because of course we know that we are creating a series of states, which we believe, so of course we can do this for an unknown state, but for our case, we are actually rotating it and creating a series of states and figuring out how it matches with what we reconstruct, right? And so then you can see that for the pure state, we have an average fidelity of, 98%. And for the mixed state, it is 95 to 96%. So most of these points, they are in the blue and the purple domain here. And this is the pure one where you don't even see any reds, which means that, you have a very, very high fidelity. Here you have a few at the poles and all, where you will have the greens also show up. And in mixed state, of course, it is understandable why the fidelity will be slightly lower than the pure state, because you see in mixed state, we have to also measure this mu. And this is the visibility, and this visibility in an measured pattern is always slightly lower than what you see, than what you would get theoretically, because you see your detector is not a point, there is an averaging involved, and so that brings the value down. Then the beam splitter has a bit of a polarization dependent transmission, and so on and so forth, so which actually explains why this is expected actually. Now, one of the interesting things with this QSI technique is the scope that it has for future miniaturization. Okay, so I was showing you an experiment which, of course, was done on an optical table with a displaced Sagnac interferometer and so on. But then now, if I actually did a double slit version of this experiment, okay, so I have two slits, and then I actually have this R on one of the slits and U on the other. So the half-wave plate and a polarizer stuck to these, then essentially within this few centimeters, I can actually get these interference patterns. So nothing else would be required. So this is just a little box with a double slit with these two operations defined at the two slits. And this is something, this sort of a thing has been done earlier for other purposes, so that it is possible to actually have this sort of a miniaturized version of a wave plate and a polarizer and so on. And so, in fact, this would be something really neat that, you have a little device in your pocket, you're just carrying it along, and, you're doing an experiment and you just put it in one of the positions and figure out what is the state at that position. And then maybe you expect that something has happened, it has changed to something else, then you put it in a new location and find out what is the state. So this is the scope that this technique kind of opens up for a future prospect of miniaturizing it in the form of a device using this sort of a geometry. Okay. Okay, so one of the other things, of course, as I was mentioning, that one of the advantages of quantum state interferography, of course, it shows up even more when you think about it from a higher than two-dimensional case. And this is something we have shown in our paper, where you will see the theory behind how this can be done. The experiment, we dealt with a qubit state, but the theory exists for the qudits. And in a sense, the idea is that for a d-dimensional state, I can actually break it up into d-1 two-dimensional systems. And so this, of course, is a lot of math, which please do have a look. And so for each of these, again, I will perform this pi 0 and sigma x in each arm, and then I will be able to reconstruct the state of this d-dimensional state as well with d-1 interferograms. Okay, and so d-1 interferograms could either involve d-1 interferometers, or we have also shown that you can do this using two interferometers and still get d-1 interferograms by this sort of an arrangement. So if they are vertically stacked, then just two interferometers will also suffice to give you the state of a d-dimensional pure state, okay, of a qudit. Now, going on to bipartite pure qubit. Now, this is very interesting because, of course, this is where entanglement will come in. And QSI, I have been able to reconstruct a single qubit state. I can do it for a single qudit also in principle. But then what happens when I go to a bipartite? So now here, I have my photon. This is just a schematic. So these are the two, let's say Alice and Bob. So this is an entangled set of particles. So the Alice one goes through one QSI setup. The Bob one goes through another one. Okay, and so what I will need is a single qubit QSI with the Alice particle, single qubit QSI with the Bob particle, and then a single qubit QSI with the Bob particle heralded to Alice being subjected to just the pi 0. Now, heralding is a concept that we use a lot in our experiments, which means that you are measuring something when some other system is expected to be doing something, okay? And so this is what is called coincidence measurement. So you have a measurement which comes in on this side by virtue of the other one being projected to something. And so here this something is when this Alice particles are projected to H, the heralded measurement that you do. So essentially it involves three interferences, right? 2 settings and 3 interferences, as opposed to 9 settings in quantum state tomography for bipartite qubit system. And of course, if you now take this to entanglement, here you can, I skip, these are the real parameters, these are the parameters that you need to measure for bipartite qubit and so on. But without going through the details, what is important, of course, is this is something we all know, that the entanglement of a bipartite qubit state is in fact given by this entanglement entropy of this reduced density matrix rho b, right? So S rho b, which is minus trace rho b log rho b. So if I'm able to actually measure this reduced density matrix, then I should be able to measure the amount of entanglement in terms of its entanglement entropy. And this is something which I can do by using a single setup. So this setup that I showed you, this is the entangled state. So by measuring a single interference pattern and a heralded interference pattern without any change in setup, I will be able to measure the entanglement of a bipartite pure qubit state. Okay, and so this is of course a great, much better and much faster way of doing this compared to the conventional tomography. So bipartite state complete reconstruction requires 2 experimental settings and 3 interference patterns in quantum state interferography. To quantify entanglement, we of course only need the reduced density matrix on one side. So this can be done with a single experimental setup and 2 interference patterns, one with Bob particles heralded to Alice's and the other with unheralded Bob particles. So in comparison, quantum state tomography would entail 9 measurements. Okay. So for Bell inequality violation, for instance, with knowledge of basis, one would need 3 measurements. So you could say that, okay, this is not that much better because Bell also requires 3. But that's not the point. Bell inequality violation is an entanglement witness. It is not a measure of entanglement. It will just tell you that whether your state is entangled or not. It won't really give you the amount of entanglement. Here I'm being able to quantify entanglement in terms of its entanglement entropy. Okay. So to summarize, the quantum state interferography can be used to determine an unknown qubit state using a single short measurement. If a bipartite state of qubits is known to be pure, then this can be used to quantify the entanglement with a single setup. With 2 interferometers, any pure qudit state with d greater than 2 can also be determined. So this definitely has a fantastic scaling advantage over conventional quantum state tomography, and it can be used for quantifying entanglement of a bipartite pure state. So essentially, we are using our age-old friend interference as a resource yet again. Okay, so this is what I wanted to say for most of the talk, but for the next 5 minutes, I wanted to give you a brief overview or a brief flavor of various other activities that are ongoing in our lab, other than, of course, this work that you saw, which is regarding using interference for various things, including quantum state estimation. And before that, I would like to thank the group of people who have constructively interfered to make this possible. Surya, Shanchari, my collaborator Arun Pati. We are, as I mentioned, we are doing a lot of work on fundamental tests of quantum mechanics. So this is our series of work in which we have tested what is called, of course, the superposition principle in interference experiments. And we have shown how this requires a correction term in terms of what is called the Sorkin parameter, and also perform the first experiment to measure this non-zero in a classical domain using an open field microwave experiment. Okay. Here we have our explorations in fundamental quantum optics. The second one, of course, you already heard about just now, but this one is our experiment on measuring what is called the Homo-Mandel dip, which is a quintessential quantum optics phenomena, and 100% dip is supposed to tell you that you're dealing with photon bunching. But what we went on to show theoretically and experimentally is that here we have generalized measurements or weak measurements as a tool, which is used to comment on what is happening to a system between preparation and measurement, which is usually not something we talk about. But this way, by doing an ensemble of measurements in a statistical ensemble manner, you can actually comment on what is happening to it in between preparation and measurement. In quantum computing domain, we are actually working with what is called higher dimensional quantum computing, where instead of using qubits, we are using our own generated spatially correlated photonic qudits. Okay, and so this is our setup where we are generating correlated qudits in the lab, and we also have new measures of quantifying their entanglement, which we have shown experimentally. Again, something which has a very nice advantage over quantum state tomography, but a completely different technique from the one you heard today. This is something which you can look at if you wanted some more popular level details regarding our work in higher dimensional quantum computing. In the domain of quantum communications, we are working on India's first project on satellite-based quantum key distribution, which is quantum experiments using satellite technology. I'll tell you 1 or 2 things about that shortly. We're working on integrated photonics-based QKD in collaboration with Italy. Quantum teleportation, again, something we all know. We are trying to achieve long distance quantum teleportation, which is another means of quantum communication. And we are also working on what is called device independent random number generation, which again is something which forms a very fundamental basis for all these applications. So whether it's QKD or something else, random numbers are very important in all of them. And so we have a way of generating them in a device independent manner, which is known to be perhaps the most random, so to speak, without depending on the devices. Okay, and so long distance QKD is very important because, of course, we don't want to do quantum key distribution just between me and my student in the lab. We have to increase this distance, and there are limitations to doing this using fiber and free space because of laws of quantum mechanics. So we need to do this in an unconventional way. And what we are approaching is using a satellite as a trusted node. We are actually increasing the distance of quantum communication. So we want to have 2 ground stations within India, which will be connected using a quantum link. And also we will have a quantum link between India and Canada, which would be, of course, several thousand kilometers, going towards what we call the global quantum internet, where, we'll have satellite as well as fiber, all will be linked together towards your long distance quantum communication. And so this is our project which is called QUEST, Quantum Experiments with Satellite Technology. And in fact, one of the things which we have recently done under this project is, actually India's first published quantum key distribution free space experiment. And so this is an end-to-end quantum key distribution experiment, which, deals with several imperfections as well, which happen in the lab. And as a result of this, we also have come up with an interesting simulation toolkit, which is able to simulate QKD, which includes imperfections, both device-based as well as process-based. And this actually garnered quite a bit of attention. This was the IBM blog. So while there are different toolkits which do exist in literature, what we wanted was something which takes into account the fact that a quantum key distribution is actually an experiment. And this will have its imperfections. The processes won't be ideal. The beam splitter won't be 50-50. And so when people come up with these simulations, they usually, are software people, right? So they don't really worry about these sort of things. But if you don't worry about them, then the key rate and error rate that you will, generate from such simulations would be not at all matching with what you would do in the lab or even in free space. And so that is why this is something we wanted to find, but we couldn't find, so we established it ourselves, which is what we call QKD Sim, which is something which you can now use to simulate QKD, including these physical process models, realistic imperfection, and experimental non-idealities. It's becoming a very interesting technology, QKD. And so, you don't want to set up an experiment and then realize you wanted to do something some other way. And so this is the kind of thing which will help in proper utilization of resources as well. And this is one of our things we have done. And these are the pictures from the lab for our QKD. And in fact, the key rate and the error we got are much, much better than what is existing in literature using similar sources. And the comparison between simulation and experiment was also very, very nice. Anyway, and now we are, of course, working on free space QKD. These are our portable ground stations. This is on top of my lab, and this is elsewhere at RRI. So we're working on a free space link across campus to demonstrate free space QKD. And, this is our portable ground station and the telescope inside, and my students here. We are, of course, having to do this currently with the current constraints, but as I mentioned, always masks cannot and should not mask our enthusiasm. So we're going ahead. So with that, so I hope I'm almost on time. And so just give you a little flavor in the end about other things which we're also working on. But of course, what I wanted you to take home as a message would be this very nice, method that we have devised of determining an unknown quantum state, both pure and mixed. Thank you very much. Okay.
Thank you so much. That was a wonderful talk.
Thanks very much.
So I guess I'll throw the floor open to any questions. So if anyone has any questions, please go ahead and unmute your microphone. I guess I'll ask a question whilst we're waiting.
Sure.
You mentioned about your fidelity rates. Are they better in your technique than the other techniques?
Yeah, so in terms of, the pure state reconstruction, of course, we have 98% on an average, and we gave you the best case, worst case scenario. So the best case is 99, and the worst case is 97. So clearly in quantum state tomography, we are doing quantum state tomography also, of course, for various purposes, and we definitely don't get better than that. In terms of the mixed state reconstruction, both quantum state tomography and interferography, the fidelity is slightly lower than the pure state. But then, as I mentioned, there are certain things which we already know why it is 95, 96. And so at least in our case, we know how to make it better. If we actually did not have to worry about a detector's finite size, we actually went for smaller pixel, maybe spend a little more resources and get to those sort of levels, then we will be able to increase this fidelity. And even in tomography for mixed state, of course, it is much, much lower than pure state. So indeed, it is comparable. But then in terms of scaling, we are, of course, doing much better. So that would be my,
Right. Right. I guess the scaling is probably optimal, right? Based on the conversation we had with Shubhro, that seems you can't beat linear scaling.
The scaling is not, the scaling for qubits in our case, of course, it is one measurement. What Shubhro was saying is the comparison between d square minus 1 and 5d minus 7. So those were the previous ones. So d square minus 1 is the most general one. But if you assume the pure state, then it was shown in that particular reference that I mentioned, that you can go down to 5d minus 7. So if you think about d equal to 2, d square minus 1 and 5d minus 7 are both 3. Right. So that is all the comparison. But for our case, it is 1. So we are, of course, better. 1 being much better than 3. Yeah. But then if you indeed wanted to see the real gain, then even d equal to 3 is enough, where of course we require 2 and any other system would require 8 with the pure state assumption. Yeah. So
I see. So would pure states with additional structure require fewer measurements? Is that?
Yeah. So pure states, that is the point. So then d square minus 1 is the number regardless so with no assumptions. Okay. But then if you make this assumption that, okay, it's a pure state, the pure state itself is an assumption, right? So of course you do not know whether your state is pure or mixed. So if you make the pure state assumption, then the best you can do is bring it down to 5d minus 7 for earlier methods. But in our case, it is d minus 1, regardless of whether it is qubit or qudit. And as I mentioned that in our case for the qubits, we can do both pure and mixed. But so far we have worked out how to do this for pure states for qudits. So ours is d minus 1 as opposed to 5d minus 7. So while 5d minus 7 is also linear, it is still as I showed that table, it is much larger in number than d minus 1 would ever be. Right? And also one more point which I kind of mentioned in a hurry, and that was this, that if you do d minus 1, so d minus 1 is the number of interference patterns you need. But we have also shown you that you don't really need d minus 1 interference experiments to do that. You can actually just do 2 interference, with just 2 interference experiments, you can actually get d minus 1 patterns. And that detail is, of course, there in the paper. So the d minus 1 is for the number of measurements, but not the number of, experiments, so to speak. So then it's even better.
Got it.
You can do it that way. It's a technological thing. I think Professor Home has raised his hand.
Yeah. Hello.
Yeah, please.
Can you hear me? Yes. Urbasi, what you spoke about miniaturization is a fantastic possibility. So I couldn't get what is the real experimental challenge involved there? It looks like would have immense possibilities. So what is the real problem?
So it is not a challenge, Professor Home. We should do that next. So the idea is that, if you have what is beautiful about this is that, see, you have double slits, right? So of course, double slit experiments are being done and we ourselves are also doing it. But then having said that, those are in the micron domain, isn't it? So these slits in the micron domain. So if you have just 1 or 2 centimeters away from the slit plane, you get the Fraunhofer limit, and so you get your interference pattern. So this entire thing can be within a box of 2-3 centimeters. And so what you need to do is, of course, this, as I was saying, that the R is in one arm of the interferometer and the U in the other, right? So how do you do that in the double slit case? So you need to have a miniaturized wave plate and a miniaturized polarizer. So these would be films, okay, which would be essentially, stuck on the first slit and the second slit respectively. But this has already been done by some groups for other purposes. This sort of small, miniaturized wave plates and polarizers have been used for completely different purposes. And so in principle,
it should be feasible.
Yeah, it should be doable and definitely feasible. I mean, of course, for our case, we have to manufacture them. We haven't done it. But then there are other groups which have done it. And so in principle, a very feasible thing to do. And then, of course, comes this thing, right? Like a little box where you just...
So it looks like a fantastic possibility. So you can...
Indeed. That is one of the... Yeah, so of course, we have done an experiment, is the first one, to show that, all this actually works. But lots of things to do for both qubit and higher D. Right, yeah.
Yes.
Thanks for the question.
Are there any other questions? Okay, I guess I don't see any other questions. I'd like to thank Professor Urbasi Sinha again. It was a wonderful talk. Thank you so much.
And of course, I would also like to thank all of you for, for this wonderful opportunity. And it makes things appear more alive, in spite of the current situation. So it's very nice. Thanks a lot.
Great. Thank you. Thank you so much. All right. Thanks, everyone, for joining us, and we'll see you next time.